1-methyl cyclohexene and limonene are cyclic alkenes with a citrus smell. 1-methyl cyclohexene is manufactured and used in the chemical industry. Limonene is found naturally in orange peel. 1-methyl cyclohexene reacts with HBr to form two structural isomers. The major product is 1-bromo, 1-methyl cyclohexane. So our major product is 1-bromo, 1-methyl cyclohexane. Name and outline the mechanism for this major product. So we're using an alkene, and so we're going to be using HBr as an electrophile attracted to that area of high electron density, and it's going to be added onto it. So we need to draw our alkene out, and then we want to use our HBr. So the double bond is going to attack the electrophile, and then we're going to break the HBr bond. Now comes the important bit. We must show the generation of the carbocation that leads to the major product. So we want the most stable carbocation intermediate. So we've got a choice. We can either put the plus here or here. We want to put it in the place that gives us the most stable intermediate. And so the place that gives us the most stable intermediate is to give it on the tertiary carbocation intermediate. Let's redraw that structure because it's, and that would be at this point here. And then the bromide ion with its lone pair can attack, and that's going to give us the product it mentioned in the question, which was 1-bromo, 1-methyl cyclohexane. Draw the skeletal formula of the minor product. So remembering back to the mechanism, we had a choice to put the plus here or here. And this time, if we put the plus on the carbon on the left, the Br will end up on the carbon on the left. And so we'll end up with this structure. And explain why the products are formed in different amounts. So the product we made on the previous page, the major product, is formed via, so from, the more stable, and it was a tertiary carbocation intermediate, whereas the minor forms via the less stable, and in this case it's a secondary because it has two carbons attached to the carbon with the positive charge in the intermediate. And be careful, it's the intermediates that are more and less stable, not the products. Tertiary carbocations are more stable due to 3 alkyl groups having a greater positive inductive effect than 2. Draw the structure of the major product when an excess of HBr reacts with limonene. So we need to go back up and look at the structure of limonene. Limonene has got 2 double bonds. So the major product, if we put HBr onto this first one, would be the same that we had before. So the Br would be at this junction, and then at the bottom, the Br would be at the junction that was also another tertiary carbocation intermediate. because if it had gone on to this end, it would be a primary carbocation intermediate. So remembering that we had a methyl group and we put a Br at this point here on this tertiary carbocation, then we had a group like this. There was a double bond on this left-hand branch here, but we're going to put the Br on the centre where it's a tertiary carbocation intermediate, giving this tertiary halogenoalkane.